Hey guys, this is Yoru. In the previous lecture, we have learned how to do velocity analysis using vector method. In this lecture, we will continue with acceleration analysis. The goal of acceleration analysis is to determine the acceleration of a particular point on the rigid body. To do so, again, according to kinematics, the second derivative of displacement vector with respect to time is acceleration vector. The derivation of acceleration vector is shown here. You might notice that there are 4 terms in the acceleration vector. In fact, they all have their own physical meaning. The first term r double dot is the normal acceleration. The third term omega dot cross r is the tangential acceleration. The fourth term is centripetal acceleration. And the second term is Coriolis acceleration. With this conclusion, now let's look at the rocket crank mechanism. In order to do acceleration analysis, we differentiate the displacement vectors r1, r2, r3, r4 twice with respect to time to obtain a1, a2, a3, a4 and end up with 2 equations. Note that since the length of each rigid body will not change at all, the terms with r dot and r double dot will not appear. Since θ1 dot, θ2 dot, and θ3 dot have been determined from velocity analysis, the system is again a single DOF system, which means after assigning θ1 double dot, θ2 and θ3 double dot can be determined. Once they are determined, the rest of the coordinates can be determined by the following relationships. The next example is slider crank mechanism. Similar to previous example, we differentiate the vectors r1, r2, r3 twice to obtain a1, a2, a3, and 2 constraint equations for acceleration. Note that the reason why we don't have the terms with omega 3 is because the slider will not rotate at all. After assigning θ1 double dot, θ2 and x3 double dot can be determined. Once they are determined, we can find the rest of the coordinates by the following relationships. Since y3 and θ3 dot are 0, y3 and θ3 double dot are also 0. The last example is inverted slider crank mechanism. The procedure is totally the same as previous examples. The only thing you should notice is that since both the length and angle of R2 will change, all the terms in acceleration vector, such as tangential and Coriolis acceleration, will appear. After the unknowns are solved, we can find the rest coordinates by the following relationships. Note that θ3 double dot equals to θ2 double dot, since θ3 dot equals to θ2 dot. So this is the end of this lecture. In the next lecture, we will take slider crank mechanism as an example to show you how to do kinematic analysis based on vector method using MATLAB. See you next time.